Hey guys, today is basically the last big chapter and it is on linear regression. So we've gone back to our chapters 6 through 8. We are going back to our scatter plots and now we're going to figure out how to do hypothesis tests and confidence intervals on these. So a quick review of linear regression. You have to remember what your LSRL is. So you have some y, so a y hat that's equal to your a plus bx, where a is your y-intercept and b is your slope. And then you have your r value, which tells you how well the model fits, and your r value is your number between -1 and 1. One more concept that you should probably keep in mind is also your residuals, which would be your observed values minus your expected value. The number in an actual data point minus the number that your equation gave you back when you plugged in the x value for that data point. So here I have a scatter plot drawn of waist size against percent body fat. And you will notice that here there's lots of data points and there's also lots of x values in this thing. So let's say that this is one x value. Let's just pretend this is all on one vertical line. So that shows us that we have a lot of data points in one x value, right? So within this group, we have a data point over here, we have one over here. So they're in all different places. Let's say that this x value is 39 inches. So this value that we took is 39 inches. If we take this cluster of data points, that will represent all the people studied here with 39-inch waists. So using that, we can actually create a histogram of people with 39-inch waists. Since there's no need to have a waist size as a variable anymore, the only variable remaining will be your percent body fat. So we put percent body fat on our x-axis, and then we have some histogram of the data points in our little column here. So this is a sort of mini histogram that we took out from within the scatter plot, and if we did it for every single other x value, so if we came over here and took another column of points and said this was the 38-inch people and created another histogram for these people, we would have a bunch of mini histograms for every x value, right? So now that we have all of these mini histograms for each of the x values, we can sort of remake our scatter plot into something like this. So there's a bunch of mini histograms lined up along our scatter plot now. Let's say this is our 38-inch people, this is our 39-inch people. So each of these histograms corresponds to a waist size measurement. And looking only at our 39-inch histogram, you can see that there is definitely a mean of this histogram, right? So each of these mini histograms has a mean. And so what we're essentially doing when we run a line of best fit through it is that ideally, we want our line of best fit to go through the mean of each mini histogram. Keeping this in mind, let's look a bit at our LSRL. So when we did means and proportions and chi-squared tests, we always had a population statistic and a sample statistic. So for proportions, our population statistic was p, and our sample statistic was p hat. For means, our sample statistic was x bar, and our population statistic was mu. So we have the same thing for LSRLs. In this case, what the population is representing is if we took all the people in the world, so every single person on Earth, we got their waist size and their body fat measurements and put them on a scatter plot. And if we ran a line of best fit through that massive scatter plot, that line would be our population LSRL. But of course, this is very hard and unrealistic in terms of if you really wanted to get it, because there's so many people on Earth and there's so many people being born every second. So instead, what we really have to stick with is our sample lines. So this is the one we're more familiar with, our y hat is equal to a plus bx, but this is still just a sample. So here is our population LSRL. So instead of y hat, we have mu y is equal to beta 0 plus beta 1 x. So our beta 0 is the y-intercept and the beta 1 is the slope. And what the mu y is representing is the mean y value for that x value. So what that means is, back to our mini histogram graph, what we're doing when we plug a number into our population LSRL, we're giving the equation a location for the x value, so we're telling it which mini histogram to look at, and ideally, it will pop back out the mean of that histogram. So again, if this is 37 inches, this is 38 inches, and this one up here is 39 inches, then if we plugged in 39 for x, so we're telling it we want to know about people with 39-inch waists, the number it would pop back out is the mean of this mini histogram. So thinking more realistically, if we went out and grabbed 50 people and then got their waist sizes and their percent body fats and plotted them onto a scatter plot, well, that is clearly a sample of the entire population. So the line of best fit that we would put through that scatter plot would be in this format. These are the sample variables for an LSRL. We have a y hat is equal to b0 plus b1 x. So this is reserved for when we have samples. The thing is, we also know that not every person with a 39-inch waist have the exact same percent body fat, so our population line of best fit isn't going to be able to run through every single point on our scatter plot. Some people with 39-inch waists might have abnormally low or high body fats, so for the purpose of accounting for all the natural variation between points, we have an adjusted formula over here. So all of it is the same except for our extra epsilon at the end. So this is an extra term to account for error and natural variation. So it soaks up all of the deviation. And what it is just an extra constant value that changes to accommodate each data point that is off from the line of best fit. So for a data point that is farther away from the line, our epsilon value will be larger in order to cancel out the variation of that point. But if a point is close or on the line of best fit, our epsilon value will be very small because that point has a small error. So here are our conditions to do inference on linear regression and scatter plots. So first, this is a new one. We have our straight enough condition. So does the plot look like a line? This one you can just eyeball and say, yeah, the graph is straight enough. These three are the same, so one point should be independent of another. So one person's waist size / percentage body fat should not affect the waist size / body fat percentage of another. You have to have a random sample, or at least a representative one, and then you have to sample under 10% of the population. Those we have gone over quite some times. Next we have our equal variance condition. This one says that there has to be an even distribution of points, so the plot can't have really major clusters or anything like that. For example, some scatter plot like this would be fine because there's no major clustering or anything. However, if we got a scatter plot that looks closer to this, so there's a lot of points over here, but they're all more spread out over here, you can see that there's a clear cluster over here. So here we do not have even distribution, and this does not pass the equal variance condition. Next is our nearly normal condition. This one is a little bit different. I know we already have a nearly normal condition for means, but this one has a slightly different thing. It says that the residual plot has to be normal. So we take the residual for every single point on our plot, and then when we put those residuals into a histogram, then we should see a normal distribution, or at least a unimodal and symmetric one. So when we plot out the residuals, it should look like this. We also have an outlier condition, which says that if there's an outlier, we probably should not do linear regression because outliers have such a major impact on the LSRL. So regression inference is not a hypothesis test, first of all. Regression inference basically is just when we have some data points, we put them onto a scatter plot, and then we get a sample LSRL for it. So we're not doing any hypothesis tests, we're just getting a sample slope, sample intercept, etc. So the first thing we do is give a POI. So what are we interested in making an LSRL for? So in the case with our running example, we would say, we are interested in doing linear regression on the relationship between waist size in inches and percentage body fat. Then you do your conditions. So these are all the big list of conditions that we just did. Our straight enough condition, our outlier condition, all that. So yeah, there it is. Then we get our information from the calculator. So depending on what kind of information you're given and then what kind of calculator you're using, what will normally happen is that you will be given every single individual data point, and then in your calculator you can put them into some kind of data table or spreadsheet. It kind of looks like a Microsoft Excel spreadsheet. And then with that, there's an option to do linear regression on it, and it will directly give you your slope, your y-intercept, your r value, your r-squared value, and then some standard errors. So the main numbers you really need are your slope, your intercept, your y-intercept, and then your r value. And then you conclude. So the conclusion here is a little bit different. Right now we're not going to be failing to reject or rejecting any null hypotheses. What we are going to be doing is interpreting the results that we got from the calculator. So we interpret the slope, the y-intercept, and the r value. So here we have some practice for how to conclude. Let's say that we have just finished step 3 and we got this information from the calculator. So we got the slope, we got the intercept, we got the standard error of the slope, and then we got the r value. So the standard error of the slope is basically saying that the calculator took the scatter plot, they gave you a line of best fit back, but the calculator says, I know that this is just a sample, and this line probably isn't the same as the one for the entire population, so I'm going to give you a standard error as well. So what that standard error tells us, it gives us a little bit of room to move around when we actually start talking about the entire population and estimating where the population slope is as opposed to this sample slope. So what our calculator is telling us is that with a standard error of 7, that means that the population slope might not be the same as this one. It might look like this or like this, but it'll be generally within 0.7 of what we were originally given, so our actual sample slope. So we can start off by interpreting our slope. So what does the slope tell us? We've actually done this in chapter 6 through 8 before. We just say what the slope means. So the slope of 4.7 tells us that for every 1 unit increase in x, there is about a 4.7 unit increase in y on average. First thing you notice is that I just said unit and x and y here, but normally in an actual question, always include as much context as you can. So actually name what your x variable is, name what your y variable is, and then include as many units as you can. And then include these terms as well, so about and on average, because our slope is again always just an estimate. Next we have our y-intercept. So the y-intercept of 23 tells us that when x is 0, y is 23. This is or is not realistic because, and then you comment on whether or not it is realistic based on the context of the question. Again, you have to do this because you're extrapolating here, and extrapolating is a dangerous estimate. We can also use the standard error of the slope in our interpretation as well to comment on how precise your model is. So you can say something like this: because the standard error of the slope is so small, it's 0.7, the estimate appears to be reasonably precise. And then finally we have our r value. We can use either our r value or our r squared value. I personally like to go with the r squared value. So going back to chapter 6 through 8, our r squared value was our coefficient of determination. And what that told us is what percent of variation in y is accounted for by x. So putting that into practice for this question, we would say something like, the r squared value of 0.81 tells us that about 81% of the variation in y is accounted for by variation in x. So it's telling us how well our model did. So now that we have our LSRL, we can look at the residuals. So since we have all these data points, each data point is some distance away from the LSRL. And that distance is our residual, of course, with the residual being our data point y value minus our LSRL y value. We have all of these residuals, one for each data point, and with those residuals, we can find the standard error of the residuals. So that is denoted with an S sub e, and that is equal to the residual, so observed minus expected, the residual squared over n minus 2, where n is the sample size. And this one tells us, on average, how far away the data points are going from the LSRL. So if we had a scatter plot like this, where the data points are really, really close to the LSRL, we have a small standard of error for the residuals. On the other hand, if our LSRL was here and our data points were all scattered around it, that means that we would have a large standard deviation for the residuals. But wait, so I basically just said that the standard deviation for the residuals tells us what kind of variation is going on with the data points. But we already have a value that does something similar, our r² value. This one also tells us how much of the variation in y is accounted for by the variation in x. So both of these talk about the variation in the plot. So which one do we use and which one is better? Each one has its own advantages. The standard error for the residuals is mainly used when we have a wide range of x values. So when we have a graph that looks like this that spans over a large amount of x values, we can probably use the standard error for the residuals and it would be okay. But if we had a plot that was more clustered around a few x values, it would be better to use our r² values. So the r² value, so basically what it's saying is that the r² value is applicable to a wider range of scenarios. So there is actually a way to hand calculate the standard error for the slope, and the three main variables involved is s sub e, s sub x, and then n. So n is the easiest one to understand, that's just the number of points that you have. S sub e we just talked about, that's the standard deviation of the residuals. Our s sub x is the standard deviation of x. So if we compile the list of all of the x values available for our data points and took the mean and then calculated the standard deviation from that, that would be our s sub x. So that just tells us how much variation we have in our x values. So the actual formula for it is here. It's the standard error of the residuals divided by the standard error of x times the square root of n minus 1. So you can use this value to standardize the slope. So if you want to get a t-score for your slope, that would be equal to your sample slope minus the population slope over the standard error, where the standard error is this big formula here. So when it's standardized, again, it's a t-score because we're talking about means here. The slope is going to fall into a t-model, and the t-model is not going to have n minus 1 degrees of freedom, it's going to have n minus 2 degrees of freedom. This is one of the only places where you will have a degrees of freedom of n minus 2. Your n minus 1 is mainly used for t-tests and stuff like that. Your degrees of freedom of n minus 2 is used almost solely for linear regression. So where else do you need this standard error for? Again, another place where we need standard error is for our confidence intervals if we want to give an estimate of where the population slope is based on our sample slope. So our confidence interval is always going to center around our sample slope, and then our margin of error is, again, basically the same thing. We have our t-score, but this time our t-score is using a degrees of freedom of n minus 2. Please remember that. And then our standard error is our formula from earlier, so the standard error of the residuals over the standard error of x times n minus 1, square root of n minus 1. So when we run hypothesis tests, we will always have a null hypothesis and an alternative hypothesis. For our null hypothesis, it will always be the same thing, and it will be that your population slope is equal to 0. Because what you're looking for in a linear regression hypothesis test is you're checking to see if there's actually a relationship between the two variables. So let's go the other way. What if there was no relationship between the two variables? So if there's no association between an x and y variable, then our scatterplot is just going to look like a big mess. So if you ran a line of best fit through here, logically speaking, it would just end up as a horizontal line. And so here, our slope would be 0. Therefore, when we run our hypothesis test will always be first that there is no relationship between the two variables. And if there's no relationship, then looking at here, our slope would be 0. So that is why our null hypothesis says that beta 1 is equal to 0. And so later on in our hypothesis test, again, we will always get that t-score with n minus 2 degrees of freedom. And so when you calculate that, your formula is always observed minus expected over the standard error. So your standard error is again going to be your standard error for the slope formula. Your observed one will be your sample slope, but what about your expected? Your expected is always going to be your assumption from your null hypothesis. In this case, it's 0. So our t-score formula simplifies down to b1 over se. Of course, it is always best to put the minus 0 at the end just to show that you understand what you're doing. So the steps for it are down here. The first thing is always to say what you're interested in finding. So what are you interested in doing linear regression on? Then you give your important numbers and your hypotheses. do your conditions. So those are all the big long list of conditions that we did earlier. And then you use your calculator to get your intercept, your slope, and then your standard error for the slope. If you want to, you can also get your R value, but it's not necessary here. Then from your calculator, you got your B1, that is necessary for your t-score, and your standard error is also necessary for your t-score. So plugging that all into your t-score formula, you get a t-score. And with that t-score, you can go and get a p-value. So the calculator function you use here, again, you're still working with t-models, so we're not introducing a new calculator function this time. It's just going to be your tcdf function, where you put in a lower bound, an upper bound, and then your degrees of freedom, which is n-2. And then with that p-value, you go to your conclusion, and this one is still the same. You just say if the p-value is greater than or less than alpha, and then whether or not to reject the null. So here we have some practice for our hypothesis test. The question basically says, we're going to see if the day the ice in a river breaks every year has changed over time. Geez, that should be okay. We have data for the day the ice breaks from the last 95 years. I'm not actually going to list it out, but I'll just give you the numbers that you need. So most of the time with these questions, because over the last 95 years is 95 data points, the thing that will usually happen is that they'll just straight up give you what the slope and then your r-squared value, the y-intercept, and then the standard error for the slope are. They'll actually tell you what those exact numbers are, but you can't just use those right away to get your t-score and all that, because you still have to show your work, such as your POI, your conditions, and then all of that. So you have to pretend like you don't know those numbers up until you get to step 4. So first is our POI. What are we interested in doing? So we are interested in seeing if the day the ice breaks has changed over time. The slope may indicate this. So why I use the word change is because this is implying that we're going to go see if there's a relationship between the years and then the day the ice breaks. Next is our important numbers and our hypotheses. This is not where we put in our sample slope and our standard error for the slope and all that. We should put that in for step 4. So in this case, for our step 2, we should just start off with our hypothesis. So our null hypothesis will always be the same thing, that our beta 1 is equal to 0. Our alternative hypothesis is that there is a relationship. So if there is a relationship, then beta 1 is just not going to equal 0, because it could be a positive relationship or a negative relationship. And then our alpha value is always going to stay the same at 0.05. Our sample size is the number of points we have. So we have 95 years worth of data, so our n is 95, and our degrees of freedom is equal to n-2, which is equal to 95 minus 2, which is equal to 93. So next is our big long conditions. Our first condition is going to be the straight enough condition. So does our data look straight? I'll just give you a scatter plot now, but you have to keep in mind that for these kinds of questions, you have to draw a picture to prove that yes, the data is straight. I'm not just pulling this out of my butt. So here's my really badly drawn scatter plot, and then for my straight enough condition, I will say this. For our independence condition, this is actually a little bit risky because global warming and all that stuff, so the day that the ice breaks one year might actually be associated with the day that the ice breaks another year, because we still want to go through with our conditions, right? So we still want to pass this condition, so we're going to say, I have some concerns about this condition, but we're still going to proceed with caution. So we obviously know that the data cannot be randomly selected because we just went through the last 95 years. We can't really randomly select years. So in this case, we're going to say it's not random, but we don't have reason to believe that it's unrepresentative. Next, we have our 10% condition. So did we sample under 10% of all of the possible years? So the Earth has been around for more than 950 years, so we're good. Next, we have to examine our residual plot. So again, for our residual histogram, we have to give an actual picture for graders to consult to prove that we didn't get our information out of our butts. So I'll just draw up the residual plot for you right now. It looks something like this. So what we say is, yes, the residual histogram is unimodal and symmetric. So for good measure, I threw in the other two remaining conditions as well. So I included the equal variance condition and then the outlier condition into one sentence. So the residual histogram is unimodal and symmetric. So that takes care of our residual histogram. The scatter plot appears to be evenly distributed, so that's our equal variance, with no outlier. So that takes care of our outlier condition. Now that our conditions are satisfied, we can say that yes, we pass the conditions and we're going to do a hypothesis test. Because the conditions are satisfied, we can proceed with a regression slope t-test. So regression, because we're working with linear regression, we're making inferences about its slope, and then this is going to be a t-test. So step 4 is just to get our information from the calculator. So our r-squared value, our y-intercept, our slope, and the standard error for the slope. If the problem already gave it to you, you can just copy it down exactly as it is. So let's say in this case that these are our numbers. So with this information, we can also write out a sample LSRL. So that looks like this. With this information, we can now go on to get our t-score and then plug everything into our calculator. So our t-score formula is our t n minus 2 is equal to our b1 minus 0 over the standard error of b1. So our t sub n minus 2, so that is our degrees of freedom. We established earlier that our degrees of freedom is 93. And that is equal to b1 minus 0. So what is b1? That is our sample slope. So that is the number we got up here, negative 0.0714, minus 0 because this is our null hypothesis assumption, and then over our standard error. So that is the number that, again, we got out of our calculator. Very straightforward. We plug in our numbers, and our t-score comes out to be negative 3.4. With that t-score, we can draw our t-model. So 0, negative 1, negative 2, negative 3, negative 4. We flag our t-score of negative 3.4, and we want this area. But because our test is two-sided, as we set up here, that means we have to multiply an extra 2 to our p-value. So going on to our calculator, what we want is the probability that t sub 93 is less than negative 3.4, and we're going to multiply an extra 2 because our test is two-sided, because our alternative hypothesis said not equals 2. So that is equal to 2 times TCDF, because we're working with a t-model, with the lower bound, the upper bound, and then our degrees of freedom. Our degrees of freedom we already know is 93. We labeled that in the subscript of our t-score. And the lower bound of this area that we're interested in, well, this goes on forever in this direction, so that is negative infinity, up to our t-score of negative 3.4. And with that, we get a p-value of 0.000989. So we have our very small p-value here, and we can now go on to conclude. If there was no change in the date that the ice breaks, the probability of the observed data occurring would be 0.0989%. Because the p-value is so freaking small, and then we do our comparison, I reject the null. So that is the end of our hypothesis test. And there is one more topic that we have to cover, which is now that we have our sample LSRL, how do we make estimates based on this equation? So what we do when we make estimates is we're basically going to make a confidence interval. With these kinds of predictions, you will likely be asked something like, make a prediction for the mean percentage body fat of all men with 39-inch waists. So in this case, you put in the 39-inch waist to your model, and then what you should get back is a confidence interval that gives a rough estimate of where the mean percentage body fat for that group of people should be. So there's two ways that this can go, and it's all going to be based off of this confidence interval equation right here. So for all of the possible cases, we are going to have our confidence interval centered around our y hat. So that's the direct number that we get when we plug our x value into our LSRL. Then we have our t-critical value. Again, we can always get this from the calculator based off of our degrees of freedom of n-2. But the one that really changes is our standard error. So the reason I didn't specify what the standard error is for, see there's nothing in the subscript here. So there's two ways these questions can go. In one case, they can ask about a mean value. In another case, they can ask about an individual point. So what's the difference? Let me state two different problems for you and see if you can spot where these two kind of deviate from each other. One question will be, so what is the mean percentage body fat for all men with 39-inch waists? That's one question. The other question is, make a prediction for the percentage body fat of a man with a 39-inch waist. Where's the difference here? You see, in the first prediction, I said all men with a 39-inch waist, and I'm asking about an average value. So for predictions about an average value, this one is going to have less variation than an individual point, which was what I asked about in my second question. So in my second question, I asked you to make a prediction for a singular man. So which one do you think is more likely to have an extreme value? Do you think you're more likely to have an individual who is an outlier in terms of his percentage body fat? Or do you think you're more likely to have a group of people that are all outliers in terms of percentage body fat? So obviously you can see that the individual is more likely to vary more in comparison with groups of people at a time, which is why we have two different formulas for standard error. When you're talking about means, this is the equation for it. So I need to specify what all the variables are first. Most of them you should recognize. Your SEB1 is the standard error for your slope. Your S sub E is going to be the standard error for your residuals, and your N is the number of data points you have. Your X bar is going to be, out of all of the data points, the mean X value for all the data points. But this XV looking thing just means the X value you're making a prediction about. If I'm making a prediction about men with 39-inch waists, then your XV will be 39. And so that's the formula, the square root of the standard error of the slope squared times how far off your predicted X value is from the mean X value squared, plus the standard error of the residual squared over the number of data points. For your predictions about individual points, so if I ask you about a singular person, then your formula would look a little bit different. So all of these terms are still the same. You have the standard error of your slope squared, how far off your predicted value is from your mean X value, and then your standard error of the residuals over N. We added an extra term at the end though. We're adding on an extra term to increase the error. So this is the standard error of the residual squared again. So we added on just to account for individual variation being higher than mean variation. So here's some practice. I have given you all of your important numbers here. And what we're going to do is construct a 95% confidence interval for all men with 38-inch waists. So we see the word all. So that means we're going to be making a prediction for a group of people. Once we see a group, we know that the equation we have to use for the standard error is going to have to be the one for means. So first of all, what does our confidence interval formula look like? So that is our y bar for the predicted value, plus or minus the t critical sub n minus 2 times your standard error. So starting off, the easiest one to find is going to be your y hat for the predicted value. So we have our LSRL equation out here, and we're making a prediction about men with 38-inch waists. So we can plug this 38 into our formula, so we get negative 42.7 plus 1.7 times a 38-inch waist, and out of that we get 21.9%. So this is our y hat for our predicted value. Next, we can go straight into our standard error, and this one is going to be for the means of a predicted value. So that value is going to be equal to the square root of, our first term is the standard error of the slope squared. So that is 0.074 squared, that's from up here. And then we multiply it with how far away our x value is from the mean x value squared. So which x value are we making a prediction about? We're making a prediction about 38-inch waists, so we plug in 38, and then minus the mean x value. So that is our x bar up here, 36.3 squared, and then plus s sub e squared over n. So s sub e is also given up here, so that's 4.713 squared over an n of 250. Putting that into the calculator, we get a standard error of 0.32%. The last value we need to find out now is our t-critical value with 248 degrees of freedom, because our degrees of freedom is equal to n minus 2, because our n is 250 and n minus 2, so our degrees of freedom, would then be 248. Using our calculator functions, that would be our inverse t function, because again, for linear regression, we mainly use our t models. And then we put in an area and a degrees of freedom. So our degrees of freedom, we just said, is 248. And for a 95% confidence interval, the area we put in is going to be 95% plus half of what's left outside, so 2.5%. So our final area is 0.975, and our t-score is 1.97. So putting that all into our formula, we get a final confidence interval of 21.9% plus or minus 1.97 times 0.32%. That interval comes out to be 21.2696 to 22.5304. So what this means, if we were to interpret this interval, is that we are 95% confident that the mean percentage body fat for all men with 38-inch waists is between 21.2696% and 22.5304%. So we talked about means. Let's finish off with a prediction about an individual person. So construct a 95% confidence interval for a singular man with a 38-inch waist. So again, our formula is up here. Our predicted y value plus or minus our t-critical value with n minus 2 degrees of freedom times our standard error. Because we're making a prediction about an individual, we're going to be using the y-hat standard error. Our y-hat predicted value is going to be, again, the value we get by plugging in our 38 into this LSRL. So that would be negative 42.7 plus 1.7 times 38. That center is going to be the same as the last question, 21.9%. And our t-critical value is also going to be the same thing, because the only value that has changed in this question has been the standard error. Because we're still talking about people with 38-inch waists, so therefore your degrees of freedom won't change, and neither will your centered x value. The only thing that changes is your standard error, so we can just copy down the t-critical value from the last question, which is 1.97. But our standard error, so that formula is going to be equal to the same formula as last time, but plus an extra value to account for extra variation. Our first term is going to be the standard error of our slope squared. So SCB1 is 0.074. 0.074 squared times the x value we're making a prediction about. So we're making a prediction about a 38-inch waist minus the mean x value, so x bar of 36.3 squared, plus the standard error for the residuals, 4.713 squared over n of 250. So I'm pulling all of these numbers out of our given terms. I'm not doing any extra math here. And then I'm adding on our extra term for error, so our SE squared. So our SE is again 4.713 squared. So here is the only thing that makes this different from our last prediction about means. So this comes out to be 4.72%. And our final confidence interval formula has been changed to this. So 21.9% plus or minus 1.97 times 4.72%. So where does this differ from the last question? You can see that the standard error here is the only term that has changed from the last question. It was 0.32% in the first case, but here it is 4.72%. So you can see that clearly an individual has a much higher variation than a group of people. And that final interval comes out to be 12.6016 to 31.1984. Interpreting that, we would say that we are 95% confident that a man with a 38-inch waist has a percentage body fat between 12.6016% and 31.1984%. And that is it for linear regression. That's actually all 26 chapters of statistics. Well done, you got all the way here. I hope you learned lots of stuff. So thanks for sticking around. Thanks for watching. I really hope you learned something. Peace.